Okay, it started.
Okay. Okay. Okay, so now I want the whiteboard.
Desktop. The display note. Double tap it real fast. Yeah. I think I got it. Hang on one second.
How can you tell?
It'll start loading. Sometimes with these, I do a hold in and then do open.
Okay.
Just to make sure, because the double clicks are kind of funny sometimes.
I think she's going to be typing it, either that or she's a program with a stylus on the monitor. So
Yeah,
like she's on the monitor, just where the camera's with it.
And do content.
Okay. So that was going to get a black
You got to
screen.
click the paintbrush first.
Yeah, that's
Whiteboard.
And then X. And there you go. Everything. See it, hear you, and everything.
Okay, guys, can you see a blank?
Yes.
Yes, we can.
Okay. All right. Well, let's get started and see how this works. All right. So 2.3 is the composition of functions. So, yeah. Sometimes the output of one function is the input to another function. So, for instance, the amount I pay in Kentucky state income tax depends on the adjusted amount of my income on my federal income tax return. And that depends on my annual earnings. So one output feeds into the other output feeds into the, the output of one function becomes the input of another function. Okay? And these are called composite functions. Okay, so if I have the functions f and g, the composite function of f and g is defined as f circle g of x, and that equals f of g of x. Okay, so this is the inner, okay, and this is the outer function, and the output from G becomes the input to F. So you find out what g of x is, you make it the x value in f, in the function of f, and then once you've plugged that in and you do the math, then that is the composite function of f of g of x, okay? Where x is the input, and we know that all x values are considered part of the domain. You determine what your domain is. And what you get when you put your input in, the output is the range of the function. Okay? So what's that saying is the range or the output of the function g of x, has to be part of the input or the domain of f of x. And I know this can be a little confusing, and you will get to know it better as you practice. It's not always set up this way, though. Sometimes we would have G circle F of x, and that is G of F of x. And in these, it has switched. F of x is now your inner function. The output, or the range of f of x, has to be in the domain of g of x. Okay, because it's going to be the input, and you can only input things that work in the domain. All right, so let's do, what did I do? Okay, so let's do an example. If, are y'all seeing this okay?
Yeah.
Yeah.
Okay, great. So if f of x equals 2x minus 5, and the function g of x is x squared minus 3x plus 8, and we want to find, we're going to find several things, but the first thing, let's go ahead and shut that door. We're going to find several things, but first thing we're going to find is f circle g of x. Okay? So we know that that's written as f of g of x, where g of x, which is x squared minus 3x plus 8, is the inner function that's going to serve as input into f of x. Okay, so let's look at the domain of both functions. Okay, there's nothing weird going on in f of x or g of x. There's no square roots, because we know square roots have to be positive in the real world, real numbers. There's no division with a variable in the denominator, because then we would know that the denominator couldn't be 0. So for both functions, the domain of both f of x and g of x is in negative infinity to positive infinity. So that's all real numbers are in the domain of both f of x and g of x. Okay? The ranges of both, since this g of x is not going to give us anything weird when it comes out, goes through the function of f of x, then the ranges are also all real numbers. So in interval notation, that's a negative infinity to a positive infinity. So the domain and range of both of those functions are all real numbers. Okay. So again, f of x is 2x minus 5, and g of x is x squared minus 3x plus 8. Okay? So we wanted to find f of g of x. So first of all, we have to do the inner function first. So we're going to find g of x. Well, g of x is given. It is x squared minus 3x plus 8. Okay? So if f of g of x, we're just going to put in the output of g of x as the input of f of x. So that's f of x squared minus 3x plus 8. So that's what we want to do. The output of g of x, which is x squared minus 3x plus 8, becomes the input, the x value, in the f function. So that is now f of x, where x is x squared minus 3x plus 8. So we know f of x equals 2x minus 5. So f of x squared minus 3x plus 8 says that every time we see an x, we're going to put the input value x squared minus 3x plus 8 in there. So that's 2 times the expression x squared minus 3x plus 8 minus 5. We're going to use the distributive law to get rid of the parentheses. So that's 2x squared minus 6x plus 16. Bring down your minus 5, and that gives us 2x squared minus 6x plus 11. Okay? So what that says is f circle g of x equals 2x squared minus 6x plus 11. So again, it might be confusing at first, but the output of one function just becomes the input of the other function. It becomes your x value. It becomes the input. And then you run that through your function, and whatever your output is, that is the value of your composite function. Any questions with that?
No.
All right, let's go to another screen, and we're going to do another one using the same values, okay? So I'm going to rewrite it here. F of x is 2x minus 5, and g of x is x squared minus 3x plus 8. It's funny, I just touched the screen with my paper and it wrote something. So, okay, so now we want to find g of f of x, okay? Which we know, well, g circle x of x. So we know that is g is the outer function and f of x as the inner function. Okay? Well, since f of x is 2x minus 5, that is g of 2x minus 5. We just plugged in whatever f of x was as their input value. And then we know that g of x equals x squared minus 3x plus 8. So then g of 2x minus 5, you would just put 2x minus 5 in for every x in the function. So 2x minus 5, we have to put in parentheses because the whole thing is squared, minus 3 times, again, the input is 2x minus 5, plus 8. Okay, are you all familiar with the shortcut to multiplying a binomial by itself?
No.
Okay, do you all know FOIL?
Yeah.
Yeah.
Okay, so let's go up here and do 2x minus 5 squared. So that's 2x minus 5 times 2x minus 5. And if we were to do FOIL, that would be the first, which is 2x times 2x, which is 4x squared. Outer would be 2x times a negative 5, which would be a negative 10x. Inner would be a negative 5 times 2x, which is also a negative 10x. And last is a negative 5 times a negative 5, which is a positive 25. We combine like terms and we get 4x minus 20x plus 25. Okay, on the side, I'm going to show you a shortcut for that, and then I'll go back to the problem, okay? When you have 2x minus 5 squared, this is a special product. I'm going to call this A and this B, okay? What you do is you take A squared minus 2ab plus b squared. Okay? If that had been a plus 5, that would be a plus 2ab. So basically, the first term in the binomial you would square, which would be 4x squared. Then you would multiply the two terms together and double it. So 2x times a negative 5 is a negative 10x. Double it is a negative 20x. And then take b squared, that's a negative 5 times a negative 5 is plus 25. So that's just good to know. All right, back to the problem. So we know that 2x minus 5 squared gives us 4x minus 20. I'm sorry, that's 4x squared. 4x squared minus 20x plus 25. Now I'm going to use the distributive law. That's a negative 3 times 2x is a negative 6x. And a negative 3 times a negative 5 is a positive 15. And bring down my 8, my plus 8. Now I'm going to collect like terms. This gives me 4x squared. I have a negative 20x and a negative 6x, which gives me a negative 26x. And then 25 plus 8, 25 plus 15 plus 8 gives me 48. Okay, so that says that G circle F of X, once we worked at the output, the input becomes the output, which is F of X, becomes the input to G of X, is 4x squared minus 26x plus 48. Any questions on that one?
No.
All right. Now we're going to do one where it says, it asks for a number, okay? So again, we know f of x is 2x minus 5, and we know g of x equals x squared. I have to go to another sheet of paper. Minus 3x plus 8. All right, now we're going to look at f circle g of the number 7. Okay? All right, there's two ways to do this, and I'm going to show you both ways. Okay? We know this is going to be f of g of 7. Okay? So first, find g of 7. The output of g of 7 will become the input to the function f. Okay? So we know g of x is x squared minus 3x plus 8. So therefore g of 7, we just put a 7 in. Every time we see the x, that becomes 7 squared minus 3 times 7 plus 8 gives us 49 minus 21 plus 8 gives us 48 plus 8 gives us, what did I do? This is a minus 21. Oh, I did minus 1. Hang on. Okay, so that gives us 28 plus 8, which is 36. So g of x is 36. So this becomes, that's the output, this becomes the input to f of x. So that would be f of g of 7 would be f of, we just found out that g of 7 is 36, right? So we know f of x is 2x minus 5, so then f of 36 would be 2 times 36 minus 5, okay, which would be 72 minus 5, which gives me 67, okay? So that says that, sorry, f circle g of 7 would be 67. Okay, we found out what g of 7 was. That becomes the input to the f function. You throw it through, and then you get f circle g of 7 is 67. Okay? Or, in part A, we already found f of g of x equals 2x minus 2x squared minus 6x plus 11. So then we could just do f of g of 7, we just plug a 7 in as the input to there. So that's 2 times 7 squared minus 6 times 7 plus 11 equals 2 times 49. Following the order of operations, we would do the exponents first. Minus 42 plus 1. That gives us 98.
Plus 11.
Thank you. Thank you. Thank you. Minus 42 plus 11, which would give us 56 plus 11, which gives us 67. You could get the same either way, but if you've already found f of x, f circle g of x, why not use what you just found, right? Okay. Again, we have f of x equals 2x minus 5, and we have g of x equals x squared minus 3x plus 8, right?
Yeah.
Okay. So now we want to, I keep doing this. All right, so now we want to find g of f, g circle f of 7, okay? Okay, we already found g circle f of x to be 4x squared minus 26x plus 48. So then g circle f of 7, we would just put 7 as the input into this. 4 times 7 squared minus 26 times 7 plus 14 would be 4 times 49 minus 182 plus 14. Wait, where did I get 14? It was plus 48, wasn't it?
Yeah.
Okay. So let's erase that. Got to get it right if I'm going to do it. Okay, so 4 times 49 is 196 minus 182 plus 48 gives us 14 plus 48.
62.
62. So that says g circle f of 7 equals 62. Or again, we could have just fed f into g of x, taken the output of that, plugged it in as x and f of x, and we would still got 62 there. How we doing? We getting it?
Yeah.
Yep. It's easy to make mistakes on these, so just be careful as you go through. Okay? All right, again, we have f of x equals 2x minus 5, and g of x equals x squared minus 3x plus 8. And now we want to find g circle g of 1, which would be g of 1. Okay? So we know g of x equals x squared minus 3x plus 8. So g of 1, again, we're working on the inner one first, the inner g of x, inner function, would be, g of 1. Well, g of 1 would give us 1 squared minus 3 times 1 plus 8, which would be 1 minus 3 plus 8, which would be a negative 2 plus 8, which gives us 6, okay? So that's the output of g of 1. So we know g of 1 equals 6. So this output of 6 becomes the input to the outer function. This is now the outer g of x, the outer function. They're both g of x. So we know g of x is x squared minus 3x plus 8. So then our output is 6, so that would be g of 6 equals 6 squared minus 3 times 6 plus 8, 36 minus 18 plus 8. 18 plus 8 gives us 26. So that says the function g of g, okay, let's do this right. G of g, circle g of 1 would be 26. So we had the same function as the inner function and the outer function. So we found g of 1 in the inner function, and that became 6 as the output. Then 6 became the input to the outer function, and when we put 6 through that function, we got 26. So that is our composite function. And one more example on this one. Again, f of x equals 2x minus 5, and g of x equals x squared minus 3x plus 8. And we want to find f circle f of x, which is f of x. So f of x is the inner function, and then f of the output is the outer function. Okay? So we know f of x is 2x minus 5. That's the output. So then we do f of 2x minus 5. Okay? Well, let's do one step in between here. Yeah, that's what I wanted to do. So f of 2x minus 5, we simply put the 2x minus 5 in as their input. So that's 2 times 2x minus 5 minus 5. We use a distributive law to get rid of the parentheses. So that becomes 4x minus 10. Bring down your negative 5. That gives us 4x minus 15. So the function f circle f of x would give us 4x minus 15. Okay, questions? No. All right. Now we're going to look at the domains of composite functions. Okay. Okay. So the first thing you're going to do is find the domains of each function separately. Okay, the output of the inner function which is your range of the inner function, it has to serve as the input of the outer function. So it has to be in the domain of the outer function. That's what we were talking about as we went through those examples. The range or the output of the inner function has to be in the domain of the outer function because it becomes the input to the outer function. Okay? Okay, so if f of x equals the square root of x and g of x equals x minus 3, the first thing we want to do is find the domain of f circle g. Okay? So let's look at them separately. The domain of f of x, let's look at that. F of x has a square root in it, and we know we're dealing in the real numbers, so the square root has to be a whole number. It has to be 0 or greater than 0, correct?
Yeah.
Okay, so writing this in interval notation, it's got to be a 0 with a bracket because the 0's included because you can take the square root of 0, going up to a positive infinity with a parentheses. Okay? Okay? We know that it has to be 0 or a positive number. Now let's look at the domain of g of x. There's nothing weird going on with g of x, is there? There's no square roots, there's not dividing by a variable, so we know that's just a negative infinity to a positive infinity. It's all real numbers. Okay? So the domain of f circle g of x, which we know is f of g of x, with g of x being the inner function, consists of values of x in the domain of g of x where g of x is non-negative. Okay? So we know g of x has to be greater than 0. If the output of g of x, okay, is all numbers, but it has to serve as the input of f of x, which is your outer function, then g of x has to be greater than equal to 0. Okay? The output of the inner function has to serve as the input of the outer function. The outer function is f of x. It's not going to take any inputs that are negative. So g of x has to be greater than equal to 0. So what values of g of x are greater than equal to 0? We set g of x. We know that's x minus 3, so we set x minus 3 to greater than equal to 0. We add 3 to both sides. X has to be greater or equal to 3. Okay? So the domain of the composite function f circle g of x is 3 with a bracket because 3 is included up to positive infinity. Okay? Because if we put anything else in G that was less than 3, it's not going to meet the domain restrictions that f of x has. So what does this tell us? It says the domain of the composite function f of g is the intersection of the domains of both functions. Okay, I'm going to call this method 1. Well, let me look at this for a second. All right, I'm going to call this method 1. Okay, method 1 was looking at the intersections of both functions. Okay? All right, let me get my functions back. F of x equals the square root of x, and g of x is x minus 3. So let's look at method 2. Method 2 says, let's look at the composite function itself. Okay? Instead of looking at them individually, we're going to do the composite. So I'm going to look at f circle g of x, which is f of g of x being the inner function, f of x being the outer function. So g of x is given as x minus 3 So therefore, f of g of x would be f of x minus 3, okay? F of x equals the square root of 3, so f of x minus 3, sorry, that's the square root of x, would be the square root of x minus 3. We just put in the x minus 3 as your input. So we know the square root must be positive. Well, let's just do that. Must be a positive value. So we know that the square root, well, x minus 3, what's under the radicand, has to be greater than or equal to 0, right? So we add 3 to both sides. So x is going to be greater than or equal to 3, which would be all values of x that are including 3 up to infinity. So sometimes it's easier to look at the composite function to find the domain than it is to look at them individually. Okay, so that is, okay, so now we know x has to be greater than or equal to 0, right? Because that's what f of x is. So that doesn't really matter. The domain of the composite function is here. So, okay? I'm done with that. This was on a different problem. Okay, so we know what you can do it either way, method 1 or method 2, whichever works for you. Sometimes one way is easier than the other way, depending on what your functions, individual functions are. Okay, back to f of x equals the square root of x, and g of x equals x minus 3. We want to find g circle f of x, which means g of f of x, where f of x is the inner function. So that's going to be g of the square root of x, because f of x is the square root of x. We know g of x is given as x minus 3, so g of the square root of x equals the square root of x minus 3. Okay, so the square root has to be positive, so x has to be greater than or equal to 0. Okay, so the domain of the composite function is zero with 0 included, so it's a bracket, to infinity. Or I could have looked at the output of f of x being the input of g of x and looking at the intersection. So sometimes it's just easier to find the domain of the composite function. Okay, that is 2.3. Any questions on composite functions?
No.
I think actually your homework on composite functions is pretty easy. Okay. Now, 2.4 is symmetry. And you're gonna find on Blackboard that I posted a link for some definitions that are going to help you with both 2.4 and 2.5 transformation of functions, and it's also going to help you, I think, in chapter 4. Okay, so knowledge of symmetry helps us graph and analyze equations and functions. So we have some algebraic tests of symmetry, and I have these on the document for you. Okay, so a function is symmetric with respect to the x-axis if replacing y with a negative y, so changing the sign of y, produces an equivalent equation. Then the graph is symmetric with respect to the x-axis. So that says that y changes to a negative y. It's going to be symmetric. If you get an equivalent equation, then the graph is going to be symmetric to the x-axis. So the y-axis and I'm just going to shortcut this, if you replace x with a negative x, produces let me tell you, marking with this marker is not fun. An equivalent equation then the graph is symmetric with respect to the x-axis. And I'm just going to shortcut with respect to the x-axis. Notice you're dealing with y's here, the y-axis, and you're changing x to a negative x. With respect to the x-axis, you're changing y to a negative y. And either way, if you get an equivalent equation, then it's respective to that particular axis. And then dealing with the origin, which we know is 0, 0. If you replace x with a negative x and you replace y with a negative y, produces an equivalent equation. Then the graph is symmetric with respect to the origin. Okay? And you're going to find out in a little bit that this is going to be an even function. And if it's symmetric with respect to the origin, it's going to end up being an odd function. And we'll get into that some more. And I think what I posted on Blackboard will help you. All right, so we're going to test y equals x squared for symmetry with respect to the x-axis. Okay? So we're going to let y be a negative y. Okay? So we know that, this is plus 2. X squared plus 2. So we know we have y equals x squared plus 2. So I'm going to replace y with a negative y and see if I get an equivalent equation. So then I have to divide out the negative 1 across the board in every term, and that gives me y equals a negative x squared minus 2. Okay? Since a negative x squared minus 2 is not equal to x squared plus 2, then the graph is not symmetric with respect to the x-axis. Okay? So now we're going to check for symmetry with respect to the y-axis. So that says I'm going to let x go to a negative x. So we start with the original equation, x squared plus 2. I'm going to let x become a negative x, so that's y equals, I have to put it in parentheses because x is a negative x, plus 2y equals a negative x times a negative x is a positive x. Bring down your plus 2. This is symmetric. So the graph is symmetric with respect to the y-axis because we got equivalent equations. Okay? So now let's check with respect to the origin. Okay? So I'm going to let x go to a negative x and y go to a negative y. Okay? So we start out with y equals x squared plus 2. So y goes to a negative y, x goes to a negative x. So this is a negative y equals x squared plus 2. Are y'all getting that funny stuff until I let my pen up?
Yeah.
It's looking like really messy. Yeah, it's kind of annoying. So we're going to divide out the negative 1s because we're looking for y. We're not looking for negative y. So we get y equals negative x squared minus 2. So this is not symmetric.
So the origin is the odd functions.
I'm sorry?
So the origin is the odd functions.
Yes, the origin is the odd functions. If it is symmetric with respect to the y-axis, it's even, and the x-axis is nothing right now to the origins. But we're going to get into even and odd functions later. I will just mention it now. Okay, so this is one way of doing it, but sometimes we can just look at a graph and tell if it's symmetric or not by visually looking at the graph, because you know, it would be a reflection of itself. If you took the x-axis and folded it over on itself, if they matched each other, it would be symmetric with respect to the x-axis, and the same thing with the y-axis. Okay, so determine visually if the graph is symmetric with respect to the x-axis, the y-axis, the origin. Okay, so here's my graph. All right, so let's look first of all with the x-axis. If I folded this graph on the x-axis, then those two lines would meet, wouldn't they?
Yes.
They're a mirror image of each other. So this is, yes, it is symmetric with respect to the x-axis. How about if I folded the graph on the y-axis? Would they be a mirror? Would not be a mirror image of each other, so that is a no. Okay? And with respect for the origin, you'd have to be able to fold it both ways and it'd be a mirror image, so that would also be no.
No.
Okay, pay close attention to this one because I think you're going to see it on your test. Find the point that is symmetric to the point (3 and -2) with respect to, we're going to look again at the x-axis, the y-axis, and the origin. Okay, now for the x-axis, we're going to let, well, if I could, I just want to erase with my finger. We're going to let y go to a -y, right? So we know the first number in the coordinate is x and the second number is y. So we're going to change the sign of y. So that's going to be 3, 2. Okay? Y was a -2. We flip the sign of y, it's 2. We leave x the same, so the point 3, 2 is symmetric with respect to the x-axis of the point 3 and -2. The y-axis, we're going to let x go to a -x. Okay? So this is going to be, we flip the sign of x and we keep y the same. Okay? And with the origin, we do both. You let x go to a -x and y go to a -y. So that's going to be The 3 changes sign to a -3. The -2 changes the sign to a +2. That's easy, isn't it?
Yeah.
You wouldn't believe how many people miss that on the test. All right, now we're going to get into even and odd functions. So an even function if the graph of a function is symmetric with respect to the y-axis, it is called an even function. Okay, and that means for each x, in the domain of f, f of x equals f of a negative, because what did we say? We said if it is symmetric with respect to the y-axis, you let x go to a -x. So the x as the input becomes x, a -x as the input if it's symmetric, okay? So you replace x with a -x. If you can do that, then you're going to get an even function. And an even function looks something like this. Okay? If you folded it's not perfect, but if you folded the graph along the y-axis, you would get a mirror image of each other. Now let's look at an odd function. If the graph of a function is symmetric with respect to the origin, and what is that? That says x goes to a -x and y goes to a -y. It is called an odd function. Okay, that means for every x, or for each x, in the domain of f, the function f, f of a -x equals a negative f of x, okay? So they've changed the -x to an x, okay? That means it's that's symmetric with respect to the y-axis, but then they changed the whole output. They changed this to a negative, so that's like changing y to a -y, because f of x is y, okay? It's your output. So it's the same as replacing x with a -x and y with a -y. Now, An odd function could look like this as an example. If you fold it over the if you fold it over the y-axis, it would be symmetric, and it's just symmetric with respect to the origin. Now, all functions don't have to be either or odd. They can be neither. Okay? The only function that is both even and odd is f of x equals 0. And many functions are neither even or odd. Okay. So even, odd, or neither. G of x equals 2x squared minus 4. Okay? So first we're going to test for an even. And how do we test for an even function? Okay, we're going to let x go to a negative x. Because remember, an even function is symmetric with respect to the y-axis. And if it's symmetric with respect to the y-axis, then x goes to a negative x. So that's the same thing as the function g of x would have to equal g of a negative x. Okay? So let's see what g of a negative x is. Would equal 2 negative x squared minus 4, which would be 2x squared minus 4. Since this equals what we started with, it's equivalent, then the function is even. Okay, so we know that the only function that's both even and odd is f of x equals 0, and it's not this one. So by definition, the function is not odd, and that's because we just found out it was even. The only function that is both even and odd is f of x equals 0. And this one is not f of x equals 0. So we don't need to test it. So the moral of this is always test for even functions first. Okay, so it's 9:14, so I'll give the example for this one on Wednesday. Do you have any question about even or odd functions? And neither.
No, thank you.
Okay, so how did this go for you all? Was it okay?
Yeah, really
okay.
well.
Okay, so after it started, it was good.
Yeah.
Okay, and in the future, well, I've taped this one. We're going to see how it does. And if you have to miss one on Mondays, I will post them, okay?
Okay, cool.
All right, I see you on Wednesday,
Thank you.
except for the ones that are going to be doing the Star Spangled Banner. All right, see you guys.
See ya.
Okay. Stop sharing. Paintbrush?
Just, what are you trying to do?
I'm trying to-
That one.
I want
To
to
save.
stop recording.
Okay. You can minimize this bar. That way it'll leave your notes up. Yeah, just hit the minus and then come back to Skype. Go to conversation. 3 dots.